So it's my pleasure. So just, I think everyone knows the meeting is being recorded. And it's my pleasure to introduce Yuri Nikolayevsky of La Trobe University, speaking on Einstein extensions of Riemannian manifolds.
Thank you, Carolyn, and thank you to the organizers to this whole idea, and thank you for opportunity to speak. It's a great pleasure to me, and I still hope that sometimes many of us will see each other face to face and we'll meet again some sunny day. And so this is a joint talk with Dmitry Alekseevsky from Moscow University. And this presentation, let me just disclaimer, apology. This presentation is not really new. I already gave a similar talk. So if you heard this before, might be pretty boring, might be even pretty boring if you haven't. But so this, we started working on this quite some time ago, and then we did this and that, and then we turned back, and actually it's not very new result, but yeah, one of the organizers made me an offer I couldn't refuse, and so I decided to speak on this one. And so Einstein extensions on Riemannian manifold. What is this about? So we will construct Einstein matrix by extension. So you're given a Riemannian manifold and you extend it, say, by dimension, and you construct Einstein matrix and on what you're getting. And of course, this idea is by no means new. This idea, well, is very popular. So what you do, we just take a Riemannian manifold and we include it in a foliation as one of the leaves, and then we somehow explain how we construct this foliation from our manifold, and we look at when the foliated space, the resulting foliated space, is Riemannian. And again, this idea, of course, is very well researched, and probably the first thing which comes to mind in relation to this is the word product. And let me just look at something which is very well known. So you take a Riemannian manifold, a positive function, you construct your product, and now if you ask yourself when the resulting metric is Einstein, you can very easily see that your N has to be Einstein, the one you started with, your leaf has to be Einstein, your fiber, and you have an ordinary differential equation for F, and then essentially you have just some number of F's which can be used, like constant T, sine, cos, exponential, cos, sine, and then you have just to arrange the constants in the correct way. And this is very well known, and of course you can look at what products with higher codimension, or you can, instead of just du, instead of just R, take here a manifold of higher codimension, and then here I refer to the series of papers of Peterson and Wiley, and just a copy of remarkable result there, and also references to the state of knowledge. Now, let me look at a slightly more general picture. Let me look just at equidistant foliation. This time we again start with a manifold N, and we take a family of metrics depending on a parameter U. And then you construct, you increase your dimension by 1, and on this product manifold, or locally if you want, you look at this metric here, and again, you ask yourself when this thing is Einstein. And here in 2000, Eschenburg and Wang found Einstein conditions, and and they express them in terms of L. And L here is the shape operator of your foliation. And you can easily see that the shape operator is just given by this formula here. So it's essentially the derivative of the logarithm of the metric, right? So and then you can write down the Einstein conditions, and then Eschenburg and Wang, they use them to study cohomogeneity one Einstein spaces. So here in N, you have a transitive group acting for all these metrics, and then the result was that if you start with one such leaf, and if you define L, which is left invariant, and if you then under some conditions, you can always extend to an Einstein metric on M. Right. Now, this was one of motivations of Dmitry and I when we started this project, and one particular case which might probably be the easiest one here is when this L, this shape operator here, is constant. And by this, I mean that it does not depend on you. It does not depend on you. It may depend. It does depend on the point on your fiber, on your N, but it does not depend on you. This was one ingredient, one, if you want, starting point, one motivation. And another one which, another well-established and remarkable construction which motivated us was the extension of a Lie group with a left invariant metric by a derivation of its Lie algebra. And let me maybe look at this construction a little closer. So suppose you are given a Lie group, capital N, with a Lie algebra and Gothic. And you have an inner product on your Lie algebra, and you have a symmetric derivation on your Lie algebra, which is here eta. Right now, let me say that the existence of symmetric derivation imposes already some conditions on your Lie algebra. More precisely, if you have a derivation whose Jordan form is real diagonal, this imposes restrictions. And then with this data, you have a left invariant metric on your group, and you can consider first at the Lie algebra level one-dimensional extension. So you add one dimension to your N, and you define a Lie algebra on this linear space. And the Lie algebra is defined using your derivation. So if you have two vectors from your Lie algebra from the initial one, the bracket is the same. If you take one from N and you take this new vector A, then you use your derivation. And then you define the, you extend your inner product. So it doesn't change downstairs, and you proclaim your vector A to be unit and orthogonal to n, right? So now you have a new metric, the algebra, and this defines a left invariant metric on the group, which is a semi-direct product of your old group and R. And then what you can do, you can define capital D, which is a left invariant operator field on M, whose value at the identity is exactly your derivation, right? And your derivation extended by 0 to the one-dimensional space. And then if you write down the metric on your metric Lie group M, it will have this form here. So you will have du squared for where u is a coordinate, is your natural parameter on R, plus the thing here. G is your metric, your initial metric on N, right? Or equivalently, you can write it like that, the expanded form, whatever. Right. Now, now, if N is nilpotent and your inner product is what is called a nil soliton inner product, then if you choose eta in the correct way, you're starting a bit your derivation in the correct way, then the resulting Lie group is an Einstein solved manifold. And here I refer to Heber and to Jens Heber and to Jorge Lauré and to 1,000 other people who worked in that. And if the conjecture of the first named author is true, remember the first name author is Dmitry Alekseevsky. So if his conjecture is true, then any homogeneous non-compact manifold is obtained from this construction. It's a solved manifold. To be precise, it can have more derivations. It may have more derivations. Right, so let me look at some properties of this construction. So if you write down your Ricci tensor, you get these. You get this. Your Ricci's can be expressed in terms of your derivation, and this is 1-1 Ricci tensor, Ricci operator, and then n must be naturally graded by eta. Now, what do I mean by this? Now, these are properties, they are not just properties, these are properties assuming that the resulting manifold, the resulting solved manifold is Einstein. So your n, your nilpotent Lie algebra, must be naturally graded by eta, which means that your derivation, remember we chose it to be a symmetric derivation. Now, more than that, it must have natural eigenvalues, natural numbers up to scaling. And then what is more, the eigenvalues must satisfy certain linear relations. There are some linear relations between eigenvalues, which, well, resembles essentially some root structure. And finally, there is only a finite number of eigenvalue types for any given dimension. By this, I mean the following. You take your n, your nilpotent Lie algebra n, and there is only a finite number of say lists of eigenvalues which are all natural, which may occur for any given dimension. Right. So all this was motivation up to this point. And what Dmitry and I wanted to do, well, we want to use the same construction, a similar construction, but we want to drop the homogeneity assumption. So everything more or less constructed like that, but we have no algebra, the start no group, no nothing, just a Riemannian manifold. And this is what we do. We just resemble the construction of a solved manifold from a nil manifold, as we just discussed. But this time we start just with an arbitrary Riemannian space. So we take N, a Riemannian manifold, and we define capital D to be a field of symmetric operators on our Riemannian manifold. And then we take U in R, and we define the deformation of our given metric on N by this formula here. So we have a family of metrics. And then we include it in the equidistant foliation. So we look at R cross N, like as a differentiable manifold, and we define the metric like that. U squared plus G by U, where G of by U is this. So if your N is a Lie group with a left invariant metric, and your D is defined from also left invariant and defined from the derivation, then what you get here is what we have seen in the previous slide. In general, this is just an equidistant foliation. So R is, well, D by du is geodesic vector and vector field. And right, so we can just write the same thing in different forms. So if locally we have pairwise distinct eigenvalues and the corresponding eigendistributions, then our metric looks more or less like that. And two things. First of all, we do not assume that our eigendistributions are integral. So when I write here G1 up to GK, well, these are just quadratic forms somewhere, right, on our distributions. So our distributions do not have to be integrable. And second, if in the probably simplest possible case, if you choose your D to be a multiple of the identity, you get back your warped product and of a very special with very special function here, and then you can very easily show that indeed your resulting metric is Einstein if and only if your D is essentially just a constant.
Yuri, may I ask you something?
Yes.
Do these eigenvalues Qi depend on the point or are constant on the
they depend on the point. Then they do depend on the point. Yeah.
Thanks.
Just, yeah. Right. Okay. All right. Now the question which, all right, yeah. And just two pieces of terminology, which are pretty intuitive. We say that our D is, our N is D stable if the Ricci operator does not depend on U. So you take your metric, you deform it with your D as explained in the previous slide. You get family of metrics, you compute for each of them the Ricci operator. It doesn't depend on U, of course, it depends on them. And we call it d Einstein if the resulting extension is Einstein. And this is the main question which we asked ourselves when this happens. And let me start with this theorem here, which gives us necessary and sufficient condition for our metric to be Einstein. So it says that the resulting metric is Einstein if and only if two conditions are satisfied, each of which is, well, the first condition contains actually two conditions. First of all, D has constant eigenvalues. So remember, well, in the previous slide, well, D may depend on the point, it still depends on the point, but eigenvalues don't. D must have constant eigenvalues. D must be, the second condition is that D must be divergence free. The divergence of D is 0. And divergence, well, just our everyday divergence. And the second condition is that your Riemannian manifold downstairs must be Ricci stable. And what is more, its Ricci curvature must be equal to this. So not only the Ricci operator does not depend on U, not only the Ricci operator does not depend on U, but it equals to something very specific. And then the Einstein constant of the resulting metric. So assuming these two conditions, we have an Einstein metric, and its Einstein constant is minus the trace of D squared. Now, let me say three things in relation to the theorem. Now, of course, we proved this theorem just by direct calculation, and it can be deduced from the corresponding theorem of Eschenburg and Wang, but still you need some work to do. Now, secondly, this second condition, condition number 2, well, it may look similar to the soliton condition. So your Ricci is the identity plus something looking moderately nicely. Well, in general, it is not. So in general, it doesn't have to be soliton metric on NG. So and just maybe at a naive level, this condition here about the divergence is too weak for this to be the Lie derivative of metric, right? So not necessarily. And yeah, oh, I promised 3 comments, just 2. So this is the theorem, and now several questions in relation to the theorem. And the first question which Dmitry and I asked ourselves was, what can be said about these constant eigenvalues? What can we say about these constant eigenvalues? So you have your Riemannian manifold, and you have a field of symmetric operator with constant eigenvalues, but of course its eigendistributions may rotate, well, may rotate. Now, what can you say about the constant eigenvalues? And again, this question was motivated by our knowledge in the nilpotent case. So let me look at our constant eigenvalues, and let me introduce this vector P, which is our which is our vector made of our eigenvalues P1 up to Pn. And here we have a construction which very closely resembles a similar construction in the nilpotent case. So let me show the whole slide with all the formulas and notations and everything. Let me then say what's going on here. So what we do, we take our P1 up to Pn, and we construct something combinatorial / linear algebraic, which allows us to express our P, our vector, in terms of a certain matrix V, which in turn is expressed in terms of P itself. So we have some implicit condition on this P. Now let me maybe very quickly go through this construction in a little more detail. So we take a Euclidean space of dimension n. So this is somewhere, it's very far from our manifold, different universe. We have Rn, and then we define a set of vectors of this form here, fi plus fj minus fk, where fi is our orthonormal basis. And all three subscripts are different. And then we take our P. And then we take our 1 sub n, which is just a vector of all ones. And then we define f sub P to be a maximal linear independent subset in here. So we take the orthogonal complement to our P in Rn, and we look at all the vectors of this form which lie in that orthogonal complement, and we choose a maximal linear independent subset of those, and we call the members of these subset V1 ... Vm, and then we organize all these M vectors in nice and neat n by M matrix with vector columns. Just have ones in the rows I and j, and -1 in row k if VA is given by this. So every vector column corresponds to one of those V's. Each V has this form. We place 1 in the i's row, in the j's row, and in the j's row, and we place -1 in the k's row. So we have a bunch of vectors, we have a matrix. And then the statement is that our P must be equal to this expression here. In particular, up to scaling, all the P's are integers. And in particular, for every given dimension, there is only a finite number of eigenvalue types which may occur. But here, compared to the nilpotent case, we need to impose a little bit extra. We need the determinant to be non-zero and the trace to be non-zero. So provided we have these and that, provided the determinant is not zero and the trace is non-zero, our P can be represented in terms of itself. Now, okay, you can say, all right, yeah, it can be. So what does that give us? Now, the first thing here is the following. You can't just take P arbitrary. If you choose a generic P, then this set F intersected with P orthogonal is empty. F sub P is empty. If you choose a generic vector, then not a single vector from this set will be orthogonal to it. So this will be empty. And then your V will be 0. And then your P will just be all ones. So if you choose a generic vector, then your generic vector is all ones, right? So really, this is a condition. This is quite a restrictive condition. So let me just look at what this condition gives in some particular cases. For example, if you only allow two eigenvalues, both being non-zero, then your eigenvalue type must only be this one. You have a bunch of ones and bunch of twos. Only this. If your dimension is 3 and the determinant is non-zero, then you only have something coming from the case of two eigenvalues or the identity. And remember, we already discussed that if we have the identity, we just have downstairs something Ricci flat, and you have the identity, so essentially just warped product. Well, it's similar to foliation by Horostheros of the hyperbolic space. This is what you get. So yeah, so the case when D is the identity is considered to be trivial. Now, if n is 4, then you have a finite number of eigenvalue types as promised by the theorem, and you can just list them explicitly. Now, let me say we still don't know whether or not eigenvalues of opposite signs may occur in this construction at all. We have no examples of these. So they are just permitted from this combinatorial theorem. By this combinatorial theorem, we don't know whether or not they may occur geometrically, right? And to this case, when n is 3, we will return a little later. So, well, what we try to do is to look at some really simplest cases and to try to identify, to classify, to understand what must be the metric on n and what must be our extension to get something Einstein in the end. And probably the simplest case after the case when our D is just a scalar operator, just a multiple of the identity, the simplest one is when we have all eigenvalues equal but one, and that other eigenvalue is different. And we looked at this case first, and indeed, if you have such eigenvalues, then you don't have too much choice. So if you apply the theorem which we have just seen, then we can either have all zeros and 1, or all 1s and 0, or all 1s and 2. You can just look at the theorem, you can see that you can't have all 2s and 1. And we looked at these 3 classes of extensions. And let me show 2 out of 3 resulting constructions. So first of all, suppose that our D is such that its eigenvalues are all zeros and single 1. We have n-1 zeros and 1, 1. Then it turns out that what you get is just your manifold downstairs splits into Riemannian product of locally, at least, splits into the product of R and an Einstein manifold and prime with the Einstein constant -1. And then after you perform the extension, your resulting M is just isometric to the product of n prime and the hyperbolic plane of curvature -1. So in this case, you get a splitting downstairs, and you get a product of something Einstein by the real line, and then when you extend, your real line becomes the horocycle of the hyperbolic plane. Right, and now in the other case, when we have many ones and single zero, the construction, well, the resulting thing is a little less understood, but more or less what we can definitely say, we get, no, I'm incorrect now. It is understood. It is, doesn't look pretty. So I will not show the theorem. I'll just say what the theorem says. So you have essentially your n downstairs, the one you started with, one which you wanted to extend. It is by itself an extension of the very same nature, but not Einstein. So what you do, you start with a Ricci flat manifold n prime of codimension 1 in n. You extend it using this construction with a specially constructed d, which is, it's not this d, it's d between n prime and n. And then you extend again. So you have this double extension starting from a Ricci flat manifold. And maybe the most interesting case is the 1-2 case. And in the 1-2 case, we have this following theorem. So let me just show the whole theorem here. And if we've got this 1-2 extension, then indeed we get to content geometry. So your extension is Einstein, if and only if n is locally k contact eta Einstein with the Ricci curvature given by this, with the Ricci curvature Ricci 0 to tensor given by this, and then eta here is a one-form dual to the unit eigenvector on n, which corresponds to this eigenvalue 2. And the metric on G is locally given by this formula here, where n prime G prime is almost scalar Ricci flat manifold, and theta prime is a one-form whose differential is omega, the Keller form on n prime. Now, if you extend by your d, your resulting metric will look like that. So you have du squared plus your large piece of dimension of multiplied by e to the 2u, this corresponds to all ones, and plus your small one-dimensional piece multiplied by e to the 4u. Right now, let me see. Let me say that this n prime here, it is not a submanifold of n. It is the space of leaves. It is the space of leaves, and we will see this on the next slide. But before even going to the next slide, let me say that we can consider this construction as being generalizing
Oh. Did we lose Yuri?
I guess.
Oh, no. Oh, there you're back. Okay.
Mira,
You want to unmute Yuri?
yes, sorry, yeah.
Okay.
I'm
Just
very
need to
sorry.
share your screen. That's okay. Just need to share your screen again.
You may turn off your camera if this is the problem.
Not sure, I'm not sure. It was all good before. So can you see the slides?
Yes.
Oh, okay, good. I'm sorry, yeah. It's very old computer, it's almost as old as I am, and so you never know who is it. Sorry. So the theorem, and well, right. So about the theorem, so if you want to look at the homogeneous, the important thing behind it, this will be for you an important algebra, which admits the derivation having all ones and a single two. So essentially what you have is the Heisenberg algebra, maybe plus abelian ideal, right? So then this n here will be your Heisenberg group, and this n prime here will be your Euclidean space. So this like space of leaves. So you have say Carnot, Carothel metric, and this is your space of leaves, right? Now here on the next slide, I mostly just explain the words from the previous slide. So what context structure is, what Einstein structure is, and how all these works. So probably if you don't work on the everyday basis in quantum geometry, maybe just to explain that you have a Reeb vector field, which is you have a Riemannian manifold n. You have a Reeb vector field, which is of constant length 1, which is first geodesic, second Killing. And from it, you construct the whole thing. You require your vector field to define, you define contact form eta from your vector field, and you require it to be contact in the sense that it's maximal non-integrable, and then you differentiate your vector field, and you restrict to the orthogonal complement, and you require the resulting operator to be an almost complex structure. And then if it is integrable, then you get a second manifold, and you get an eta Einstein manifold if your Ricci curvature is given by that. And this is more or less the analog of Einstein manifolds in contact geometry. And then the equivalence of 2 and 3. Now our theorem is purely effect of contact geometry, which is a well-known one. And again, the idea here is that n prime g prime is the space of leaves. So again, look at say Heisenberg group at the vector field, which is defined by the center integral curves and the space of leaves factor of your group by this action. And let me maybe look at the next slide. So two remaining things which I want to say, and I will stop there. So first of all, low dimensional case. What can we say about the low dimensional case? Now, here, if you start with something of dimension 2, then you essentially get only one thing from this construction. Your dimension 2 thing must be flat, and your D must be the identity. So if you perform this construction on a 2-dimensional manifold and you want the resulting space to be Einstein, then you just have flat downstairs and the identity. So you just get hyperbolic, well, you get 3-dimensional space of constant negative curvature. Now, what struck Dmitry and I here is that in dimension 3, of course, understandably, pretty low dimension and limitations, all that bad. What struck us really that the condition of being Einstein implies homogeneity, So far we just resemble the homogeneous construction. We never imposed any assumptions. We can no group, no nothing, no isometries whatsoever. However, if you perform this construction on a 3-dimensional manifold, then the resulting 4-dimensional Riemannian manifold, Einstein, if everything is homogeneous. So Einsteinity implies homogeneity. And this is probably the most, at least for us, the most interesting, say, moral consequence of this theorem. And the concrete cases are listed in this table. So it says that if you start with something 3-dimensional, then your 3-dimensional must be just a solvable Lie group with a left invariant metric, and D must be left invariant and constructed from a derivation and the identity. And then we have this list of possibilities for the eigenvalues for N and for the resulting space, right? And finally, the last slide for today. Well, suppose we start with a Lie group, and suppose D is left invariant. Is it so that this construction returns us to what we started with? Now, the difference from what I'm doing now and from the different bit and from what I started with is that we do not assume D to be a derivation. D is just something left invariant, right? And unfortunately, we are not able to prove this in full generality. Maybe this is not true, but under some conditions, it is true. So either, say, the killing form of N is non-negative, and then D is a symmetric derivation, or we have a decomposition or orthogonal sum of cell algebra is something nilpotent, and we have two smaller conditions here, in which case D is not necessarily a derivation, but it can be constructed from a derivation of some other solvable group, which is isometric to this one. And in both cases, we get an Einstein solved manifold. And I think, oh, this is it. Sorry, yeah, this should have been thank you on this slide. So thank you. Thank you. And please, questions.
Are there questions? Mm-hmm. Thank you, Yuri.
Thank you.
Are there questions?
I do have one question.
Uh-huh.
Yeah, so Yuri, you mentioned that the condition of on the Ricci curvature of the fibers does not imply that the fiber has to be a Ricci soliton. But what about in the symmetric, in the last slide case, like when n is a Lie group?
So this one, right?
Well, any nilpotent Lie group, right? Then it has to be a soliton, right?
Yes. Yes. Yes.
Okay, but if in more generally, if it's not, I think this family still gives you a Ricci flow solution, a very particular Ricci flow solution, right?
It may be.
Up to normalizing, because I mean, you're saying that the evolution is given by the Winner-metric. Yeah, so I think it's still a very particular Ricci flow solution.
Yes, yes, it very, it very much can be. So, yeah, now, first of all, yeah, so if you have nilpotent, then yes.
And this derivation, yes.
And then for what you are asking, yeah, so you differentiate, yeah.
Because D is a derivative of the metric morally, right? Of this one parameter family of metrics on N. And you're saying that this derivative is the Ricci curvature. So up to normalizing, this should be a Ricci flow solution. I wonder if, you've noticed that, or if it's of any use. But